1 cubic centimeter weighs 1 billion tons. What would happen if we brought a spoonful of neutron star back to Earth? Neutron stars have the second highest density in the universe after black holes. 1 cubic centimeter weighs up to 1 billion tons, equivalent to compressing Mount Everest into a grain of sand. If Earth became a neutron star, its volume would only be the size of a grape. A typical neutron star has a diameter of only 20 to 30 kilometers, with a mass 2 to 3 times that of the Sun. It's the end product of massive stellar evolution. At this point, the compression force inside the star has already crushed atoms, forcing electrons and protons to merge into neutrons, thus creating the superdensity of 1 billion tons per cubic centimeter. Osmium, Earth's densest metal, is only 1/5 billionth the density of a neutron star. But once neutron star matter leaves its parent star's high-pressure environment, trouble begins, because neutron stars maintain density through extreme gravity. Without gravitational compression, neutron matter would rapidly expand, like a released compressed spring. Assume this cubic centimeter of neutron star matter remains intact. 1 billion tons of mass equals 10 Mount Everests on Earth. Earth's gravity is far weaker than a neutron star's, so this spoonful would fall at tremendous speed, like a massive meteorite crashing toward the ground. If it landed on solid ground, it would instantly penetrate the crust and drill into the mantle, cutting through like a knife through tofu. All solid matter on Earth would be less dense than air compared to it. 1 billion tons concentrated in 1 cubic centimeter would create local gravity far exceeding Earth's average. Nearby objects would be drawn toward it, creating a small black hole effect. Another possibility is, the moment neutron matter reaches Earth, it would decay into protons and electrons, while releasing enormous energy. Scientists estimate the energy released by decompressing 1 cubic centimeter of neutron matter equals 250,000 tons of TNT, explosive power 16 times the Hiroshima atomic bomb, enough to instantly destroy a city. If an entire neutron star came to Earth, the energy released would exceed Earth's binding energy, meaning all matter on Earth would disintegrate from a planet into a cluster of asteroid fragments in space. If no explosion occurred, at least 1 billion tons of matter would continue sinking. Earth's crust is only 30–50 kilometers thick. The mantle extends 2,900 kilometers deep. Their density compared to neutron star matter is thinner than air. So, neutron star matter would fall directly near the core and remain stable there because the core exists in a weightless environment. However, this is merely a thought experiment because the nearest neutron stars are thousands of light years away. Voyager 1 has traveled only 0.002 light years in 47 years. Even if we reached one, sampling and returning neutron star surface material would be impossible, because neutron star matter is virtually the hardest substance in the universe. Theoretically, only quark stars are denser. Beyond that would be black holes. In about 6 billion years, the Sun, expanded into a red giant, will gradually disperse into a nebula. The original solar core will become a white dwarf. Its density is less than a neutron star's, but each cubic centimeter can still weigh about 10 tons. The water droplet probe in the three-body problem is essentially a piece of metal with neutron star density, but normal mass, utilizing strong force interaction. So human warships are like paper before it.